I'm very happy to introduce Tatiana for our invited talk series today. Tatiana von Landesberger is a professor of visualization at University of Cologne in Germany. And before that, she was for multiple years head of a junior research group in Darmstadt. And then she held other positions after that before being promoted to full professor. And her research focuses on InfoVis and visual analytics, in particular on networks and spatio-temporal data in various applications, including medicine, biology, finance, transportation. And Tatiana's work on disease spreading has also been awarded at WIS, I think, last year. And today she's also talking about a related topic. And I'm really looking forward to the talk, Tatiana. And now it's your turn. Thank you.
Thank you, Mark, for the introduction, and thanks to the Institute for this invitation. It's my honor and pleasure to present our work that we have done in a couple of years in the area of disease spreading. And yeah, we have followed this avenue of research for the last 4 years starting in the area of infection contagion in hospitals. This was long before COVID came and Corona crisis came, and this topic has become popular. So I will try to present you several facets of this research, and also differences to most of the works that are being done in the area of disease spreading and disease visualization. Yeah, our work started with the common problem around the world about multi-resistant pathogens within hospitals. We focus on patients that are in hospitals, and when they are in hospitals, they can acquire hospital infections, and especially multi-drug resistant pathogens such as MRSA or Escherichia coli, and so on. And this problem is very acute. This was saying before Corona. In Germany, for example, each year 300,000 people get infected by the disease, and 10 to 20,000 patients die from these diseases. So this is a problem that is that has been long there before Corona came, and these pathogens can be coming from outside the hospital, but once a patient is within the hospital, they can spread among the patients, and this poses risks to patients because they are already ill when they are in hospitals, and we want to know how this disease are spread and how this can be monitored and how this can be stopped. Basically, the disease spreading within hospitals can be stopped. And this is maybe the most difference to the Corona crisis. In a Corona crisis, we all, because it's such a huge pandemic, we talk mainly about hundreds of thousands of people and numbers, cumulative numbers and aggregated numbers. But when we talk about hospitals, it's like the ship. It's like a closed system where each patient is important. We need to know about each individual, whether he or she is infected or not. It's not about the cumulative numbers, but it's about really person by person cases. So this makes a huge difference to how we visualize and analyze this type of data. And we have a long cooperation with several hospitals in Germany, mainly 7 hospitals that are parts of our consortium and work on this topic. And working on this has become three main tasks that we want to solve. And one is, how has disease spread? So once we know that there is an outbreak, we want to know how this was done before. So this is the work that we presented last year at WIS. So basically going back to the patient zero. So how has the disease has spread and what has happened? So, and the second task is how will it spread within the hospital. So we always talk about this type of this hospital person, namely who will most probably be infected, how fast will disease spread, in order to know who to isolate and what kind of measures can be done in order to stop the disease within the hospitals. For example, rooms, to disinfect rooms, or to disinfect stations, or to close stations, or just who is endangered and should be isolated. And the third thing is, this is something similar to Corona, is we can't test everybody every day. Even within hospital where we have, I don't know, hundreds or thousands of patients, it's impossible to test everybody. For example, when we talk about pathogens, there are hundreds of them. So we need to test for each pathogen. It's not only testing for Corona, but when we talk about pathogens, there are hundreds of them. So the test is very, very costly. And also patients. I mean, if you go there and every day you make a blood test, that's not feasible simply. So we need to know who is likely infected and how to get these people in, like how to identify who is likely infected. And this is a workflow that is done mainly by infection control experts that make this type of work every day. And the data source that we have is patients' contacts and disease state. So we have many records about each patient, where this patient is located in the hospital, and when and for which pathogen he or she has been tested on which day. So we have the patient status and we have the location. I will talk about limitations of this type of data in a short while. And the second one that we can use is results of models and simulations. So we have infection model like SER model and their changes, and we have also artificial intelligence models which make predictions who is likely infected and who is not likely infected. And even within one single hospital, this is a real data from one German hospital. We have more than 300,000 patients over 6 years at 30 wards, so stations. And I think there are 8 buildings, 30 wards, and more than 500 rooms where patients can be located. And within rooms, it also there is a difference in which part of the room the person is. So still within one single hospital, it's still loads of data. And this is how the data looks like. We have up to 1 minute up to 1 minute data who has been where. The problem with this data is that basically it's manually. Because of the German DSGVO and all the things around it, there is no tracking of people, but this is in the system manually. So we have, there is also temporal uncertainty when people were exactly where. And based on that, we can say who has contact with whom. And having contact means being in the same room at the same time, or being in the same room after each other, because it can happen that one touches I don't know, a table, and then another patient comes and touches the same table. So there can be a disease transmission, even if their people were after each other within the same room. And the second source of data that we have is the tests. So we have data about who has been tested when and for which pathogen. As I said, there are more than hundreds of pathogens, so not each test is for every pathogen. So we have also uncertainty about the infection status. So basically, on the day when person was tested, we know what the infection status was for this particular pathogen, but for example, somebody who is negative for one pathogen can be positive for another pathogen and the other way around. And also, if he or she is negative on one day, we don't know whether he was infected the day after. So there is loads of uncertainty. What we have is a great team of infection control experts that are within our project. And they need to analyze this data. And this is highly subjective and highly prone to additional domain knowledge. We have been talking to them for the last 4 years, and I'm still not an infection control expert, because there are so many things that need to be taken into account that are not within the data in order to be able to interpret the data. So yeah, this additional domain knowledge and subjectivity of insights, like we have 7 people and they have 3 different opinions. So the meetings are very, very long with long discussions about to find like, yeah, common understanding. And for example, an easy question could be, given the infection probability, which patients should be preventively isolated. It's also there is no rule to that. It's something that it's based on human decision, human knowledge, the infection status knowledge, and there are many other factors such as yeah, how big is the hospital and so on. So there are many things that that need to be taken into account in addition to the data that we have. And such as the role of wards in hospital, is it an emergency, or is it ICU, or is it another type of ward? So there is lots of human knowledge that is not captured in the data. And what was very surprising to us, that all these different tasks and all these huge amounts of data has been, before our project came, this is a screenshot of a real system that is used or was used. This is like scrolling for ages. It's basically a long table of all patients and their wards and their results. When I saw that, I was like, okay, we really need to do something about it. And nowadays there is a lot of work due to thanks to Corona. Lots of visualization are there. Before Corona, there were only few research in this area, and mainly, but this is also what we see currently now on this aggregated level, like how many people are infected or should be infected. What is the model saying predictions for the next year on the aggregate level? What we really need is something on a patient-by-patient level. So this is the 3 questions that I posed is how the disease has spread, how the disease will spread in the future, and who is potentially infected are the 3 works that I would like to present in more detail. And the first one is the retrospective one, the search for patient 0, which is a visual analytics system that we developed together with all other people in the consortium for analyzing the for analyzing the data. So the first task was to detect whether there is an outbreak or not. So this is already a question that is highly subjective. There are no rules depending on the pathogen. 5 people having Escherichia coli is nothing, but 5 people having Klebsiella pneumoniae is an outbreak. So it really depends. And also, are they in the same ward? Are they on a different ward? So already having an outbreak is not easy to detect. And once we detect an outbreak, we need to reconstruct the transmission pathway and determine where this outbreak takes place. Is it in a whole hospital or on a ward? Because then we can, for example, disinfect a ward. And how long is the outbreak gone? So, for example, it can be weeks or months till the outbreak is detected, and identify who is infected by the outbreak. And this has also something to do with genome analysis, because not two people who are in the same have the same test results can be part of the same outbreak. They are part of the same outbreak only if the genome of the pathogen has the same value. So this is a complex issue. And for this purpose, we developed a new visualization tool that shows on the first is the epidemic curve, meaning the number of people who are infected by a specific pathogen in the whole hospital or in the same ward. Then we have the contact network stating who has contact with whom and where could be a possible transmission of pathogens, depending on whether the people in the time of contact were infected or were not infected. Then the main view is the transmission pathway view that contains all the information about who is where, at which location, is he or she infected, and who could infect whom. And then we have the patient timeline view, which shows the detailed information about each patient. So it's the most detailed view for selected patients, where they were, at which station, which test result, are really into high detail of the test result. So, and this is this supports all the tasks that we mentioned, and combines them in order to be able to present the data that we need. I would like to show this in a small video, and I hope this works. So this is a workflow that could happen when analyzing the data. So first, this use case was done together with an hygiene expert. So analyzing where the infection was, at which station, and then showing each patient is one line. So the color of the line states whether the patient was infected or not, and the x-axis is time. What was also important for us was the difference between whether people are in the hospital or are at home or are temporarily at home. So there are people who come from home to hospital, and they, for example, they go home temporarily for Christmas and then they come back. And there are people who leave the hospital and never come back, or there are people who don't leave the hospital. And so this was one of the requirements that we had to know, okay, who is in the hospital and who is not in the hospital and who is coming new to the hospital. Because one of the tasks is also to know, is this infection acquired at home or is it acquired in the hospital? If somebody gets infected at home, we can't control that. But if we want to control only the diseases that are acquired in the hospital. And then we can see on which ward people are. So the background color states that these people were at the same ward at the same time. And if the lines are close to each other, the people had contact at that ward. So already like that, we can see that there are more and more people coming to the same ward, for example, and then they get infected at that ward. And what was a very high value added for the analysis was this tracing of infections. So the tracing of infection allows us to see who is the more or less who is the source of the infection and who this person could infect. So these lines that we see, the arrows that we see, show the source of the infection and the potential influence, like who could be infected when, by whom, basically. And this was a very, very high value added in the analysis. And this we can do forward tracking or backward tracking even via several people, saying, okay, who is going where at which station. And also like that, we could trace the second and third level contacts. That was not possible before. In the patient timeline view, we can see more details about patients, for example, when they were tested. It is difficult to imagine, but the long vertical lines mean tests. And as you see, that there are people who has been in hospital for months and have never been tested. So they could have been infected long time ago, but they were never tested. And like that, we also could see who could be tested. And with the contact network view, we can say, okay, who has contact to whom? And for example, identify a person who has contact, who is ill and is this infected and has contact to many other people who are not infected. So we know, for example, who should we test based on the contacts. Yeah, and we applied it to a large real data from the German hospital, anonymized data about 180,000 patients and 900,000 microbiological data. And we could analyze the outbreak of Klebsiella pneumoniae. And this was anonymized data. And the interesting thing was that we could reproduce this outbreak, and we could confirm what they manually, they spend months to reconstruct everything. So we could reconstruct that and could also find more information that was there before. For example, thanks to the additional analysis of genome data, for example. So like that, we could search for sources of infection. And also, as I said, thanks to the by individual patients, and also to analyze the genome analysis and separate two outbreaks that was not there before. And also what was value added was, as you see here, we could trace infections also over several words, which was not possible before. Before this analysis was, because it was so manual, it was only for one single word. Interesting was the user feedback. We could get 25 domain experts to analyze it and find these analysis and get these views, and this was something very new and very useful for them, and highly interesting and highly useful, and we got only positive feedback. And thanks to this very positive feedback, basically when we finished this work and when we were finishing, we were writing up. We finished the work already before the corona started, but we were writing up this work during the first lockdown. And this was the start of our current project, when we use this technology also to corona patients, patients in hospitals. In corona, we have a live demo. That is, we have a SMIX system currently running and being deployed in 25 hospitals around Germany. And a demo is running also online for COVID data. These are anonymized, very small anonymized data. So this is something that is, that is also very challenging in this type of work, because we need really patient data, and really this is the anonymity is a high problem, and makes our work quite difficult. But if you like, there is a live demo, and we are currently working on that on the COVID data. And as you see, the views are the same as before, and there is a corona station, for example. So there were several specific needs for the corona crisis, like we have a COVID station, differentiation between emergency unit and ICU unit, and pathways through the hospital between these type of specific stations that that was not there before, or analyzing symptoms of the patients. So there are several extensions to the previous work that we have. Second work that we did was the forecast of infection in hospitals. The question was, if we have one person that enters the hospital who is infected, how this infection could spread through the hospital. And for that project, we used the same data as before, but now we didn't do the retrospective analysis, but forward analysis. So what will happen? What could happen in the future? And the question was, how many patients would get infected? How fast would it last? And which station could then be infected? And for that person, we used Monte Carlo's simulations about transmission probabilities. So having one data set with patient contact, we could run 1,000 simulations, and each simulation led to a different result. And the question that we had was how to visualize these results, especially the uncertainty and possible scenarios about future outbreak. Because even if we have a contact of 50 patients, 1,000 such contagion graphs would not fit on the screen. One idea was to aggregate everything, so put everything on top of each other and to see the probability of each patient to be infected. This probability, however, is not enough. This type of aggregated view doesn't show us when, for example, when will the person be infected? So how much time do I have to isolate this person? How likely will I get infected, and by whom? So where should I cut the transmission pathway? So, and the time component is not there. So for the time component, we could do the infection rates and the views that we know currently from Corona crisis, but this also doesn't show you the transmission pathways. And this is something that we were very interested in. So what we did was we used hierarchical clustering over the transmission pathways with a specific similarity function and depending on the pathways. And when we use these pathways, we could find, in fact, 4 different scenarios of this transmission. When we see on the right-hand side, we see that there is a probability of 10% that nothing happens. There is a probability of 10% that 3 out of the 4 wards will get infected. There is a probability of 25% that the whole hospital gets infected, and there is a probability of 25% that only 1 ward gets infected. And this could not be seen on the global level on the left-hand side. So this is something that is very important to see what is going on. And in order to see more details, we created a new visualization to really go also into more detail on each individual patient. So who will infect whom, with which probability, in which view. So this is the aggregated view on the infection. And what we did was each patient got more or less one space on the screen. And then depending on when these patients get infected, we duplicated them on the y-axis. So y-axis is time. So we could see, for example, this N0, so patient 0 was infected only once. At the beginning, the patient 1 was infected once in step 1 and once in step 2. And the patient 2 could be infected in step 1, 2, or 3. And the patient 4 gets infected only in step 1, for example. And then we can say with which probability who gets infected with which probability in which time step. And we could see also add more information about who could infect who. Yeah. And like that, we can make really infection pathways and probabilities of getting infected and getting infected from whom at which point of time. And this is very important because if I want to decide who should I isolate, yeah, on a person level, I need to know with which probability this patient will get infected and who is the contact person, so that I know what should I change in the infection in the room allocation of the people, and how much time do I have with which probability should I take steps in which probability in which point of time. So this we applied this to a hospital, the same data, the same hospital, and this was very interesting for the people because they didn't know that there were different scenarios, and like that they also could identify patients that were kind of multi-spreaders and patients that basically need to be taken action upon very soon, and also other patients that that were highly infected or highly susceptible to be infected. And this was something new and very interesting. However, one great limitation of our work was that it doesn't scale. It works for 50 patients. It doesn't work for 500 or 5,000 patients. The scalability is a huge issue here. So it always depends what do you need it for. The third work that I would like to show you is in the area of explainable artificial intelligence. And it is about probability of people being infected. As I mentioned, there is it's a very high cost to test everybody every day. So basically what really needs to be done is to know, okay, where is outbreak? So where do I need to be aware with which probability there is an outbreak, even though I don't know about it, right, from the figures? And which patient should I test? Which word has a high probability of infections, and so on. So for that purpose, we used artificial intelligence neural network models to model the probability of diseases, and also a probability to find out the transmission pathways. I haven't talked about it by now. However, one of the more also interesting things is how these diseases get transmitted. Yeah, so what are the factors that underlie the transmission process? So if I have patients that I know that there is a transmission and there is infection, the question is, what are the features that lead to this probable transmission? So do I have words with high probability of infections? Who is likely infected? And how and when the pathogens get transmitted. And for this purpose, we combined recurrent neural networks, a model that allowed us to model the probability of diseases and also gain us features of transmission probabilities. And we combined that with interactive visualization in order to explain how the diseases get transmission and what is this model doing. We know that the doctors and infection control experts that we work with, they are not domain experts in artificial intelligence. So they need to use these model results and understand how these model results come true. So we trained a recurrent neural network that provides us a probability of infection for each person for each day, and also gives us factors of being transmitted. We have kind of 20 features that we analyze, and there are more or less 3 groups. One is type of patient state, the location, and number of infected people in the same room, so the contacts. The more contact I have with somebody who is infected, the higher that was our hypothesis, the higher the probability of infection. So there are more or less 20 features, but there are these 3 groups of features, and we trained it on real hospital data for one pathogen. And the results were very interesting. From the training, I go back to the training data. The thing is, even though we have data about 300,000 patients and 6 years of data, it's very, very difficult to train these type of models. And this is something, in my view, not many people talk about is rare diseases. So we talk about like kind of probability of being infected is 2.5%. And so there is a huge bias in the data between the number of tests that are negative and the number of tests that are positive. And this makes the training very, very difficult. So we had to reweight the data and had really large problems with biases. So the amount of data is not the problem. The problem is this imbalance between the positive and negative training examples that we have. So, yeah, it's already the training is a challenge. And the second challenge that we had was to visualize this type of data. So we created a new visual interface to show the data, and it has several parts. The first one was to show the quality of the model. So there is a standard confusion matrix with true negative, true positive, true negative, false positive, false negative. This was, however, not enough for our case. We had to extend this confusion matrix because not everybody is tested. So we can have what we call false positive and false positive errors, because we can have something that is false positive, but we can't really say because this person was not tested. So we had to extend this type of matrix and make a distinction between who was really tested and do we really have this type of information to say is true negative, true positive. The second was not only for the whole hospital, but this type of confusion matrix also for each ward in the hospital, because there are some wards where we have high number of true positives, high number of true negatives, high number of patients and low number of patients. So we needed to have this information also for each ward, not only for the whole hospital. Also, we needed this information over time. We trained the recurrent network for each time moment. So for each time moment and we have the true negative and true positive information. And like that, we could see whether our model, whether there were time ranges where the model performed better or time ranges when the model performed less good. And also time ranges where there was a high probability of outbreak and time ranges where there was low probability of outbreak. And all these views are linked. So the interactions in each view is propagated to the next view. And then once we knew that there is that we could identify potential transmissions, we could also look at individual person and look at why does the model think this person is infected. So what is the reason behind thinking behind the decision of the model. So here we see the extension of the view that we had before, and it shows the hypothesis, the probability of the hypothesis. So the darker the line, the more likely this person is that the model thinks that the person is infected, and also gives us information about how many contacts at that point, for example, the person had. And also we have features that tell us something about why this person was infected. So what was the reason of getting infection? So for example, change in the change between locations could be the reason. Yeah, so basically you acquire the disease in one room and you go to the next room, or for example rooms. Yeah, then if the reason for being infected is the room ID, then we know we need to disinfect this room, for example. So these features, they tell us something about why the infection was transmitted and what should be done with it. And we applied it to real data, to vancomycin-resistant enterococcus in a large German hospital with more than 80,000 patient cases, and trained on 80% of the data with a high probability of the result. And like that, we could identify the reasons for infections and so on. So this is basically the view that we showed before, that I showed you before. So this is the work that we have done. I look at the point, it's 2:45, so my talk should come to the conclusion. Yeah, I try to show you the whole variety of work that we do with respect to disease, visual analytics of disease spreading from backward via future work up to explainable artificial intelligence and modeling for probability of diseases. And this work is now continuing also with corona cases, and our next challenges are deployment, acceptability of this for future. This is something we talk about all the time in research, and yeah, let's see how this goes to the future. I thank you very, very much for the invitation. Thanks for your invitation and attention. And I'm ready to answer your questions. Thank you very much.
Yeah, thank you, Tatiana. Great talk, super interesting work. Thanks. Are there any questions? Or I'm sure there are questions. Who wants to start? We have a few minutes for questions, of course.
I got started.
Yeah, go ahead.
Tatiana, good work. I am curious, you have a lot of data in there, and like me working in the US, it's always very, very tricky to work with patient data because of like HIPAA compliance and anonymization and so on. And I'm assuming that this is maybe even worse in Germany with all the like privacy laws and so on. Can you kind of comment on, is there anything specific that you do to kind of like de-identify the data, or do you have agreements with your partners that you have fully identified data? Like, for example, we always have to, like, we cannot even have de-identified data on our own computers. We have to remote develop in like a secure environment, which is very, very time consuming and annoying. Like, what are your parameters there?
Thanks for this great question, Alex. We have the same problems. We were very, very lucky to be able to work with this one hospital that gave us anonymized data to work on them locally. With all other six hospitals, we need to work remotely, as you say, and in the same manner as you say, in this very closed environment and high number of I would say formulare and agreements and special PCs and special tunnels and special environment up to, and it can always get worse, Alex, up to the time when Corona came and we had to develop the system that I presented. We developed basically within 2 months in a environment that I call blind programming. So we were not able to see the data at all. So basically we created code, then somebody else tested it in the hospital and told us, okay, this is a bug and needs to be tested. And we had no clue where this bug comes from. It's a nightmare.
Do you ever work with simulated data then, or?
Well, the modeling that I told you, the predictions that were simulations, we don't have, by now we don't have the simulated data. It's a challenge. It's a huge challenge. Or we have, as you see in the demonstrator online, we have the data about 6 patients that are more or less fake data.
Yeah, okay. Thanks.
But it's a challenge, yes.
Thank you, Alex. Erich?
Yes, I do have a question. Thank you very much for this very nice talk. So I'm not sure if I missed it. In your model, you always were modeling the infections between patients. But I guess patients are a bit more stationary than doctors or nurses and so on in hospitals. Do you also have some models for those people? Or some idea how to tackle those?
I'm not sure you want to wish to have the answer. What shall I answer? It's a difficult topic, yes.
Okay. Okay, so it's up to research, I guess.
I don't think this is a technical challenge.
Okay.
Mm. Yeah. Okay, may I continue with one question? So, do you think the work, in particular the first work you were showing, could be applied to contact tracing purposes for Corona, like this retrospective analysis, who infected whom?
Yeah, this was something that was the first thing that came to our mind when all the tracings apps started.
Yeah.
I would say 2 things. I'm not sure how it's, in my view, many things that are technically possible are not possible because of the data in the end. There is the German tracing app that basically traces only anonymized data, so you don't really have the full information. And second thing, our approach has scalability issues. So we could use it for 200 people to show and trace 200 people. On this type of level of detail, you can't trace 400,000 or 80 million in Germany. So the visualization has a scalability limitations. So yeah, scalability.
Are you working on a more scalable version?
We don't have the data for that, so it would be very interesting. However, we don't have access to the tracing app data. So
yeah. And then I was wondering, when you were showing this, like the spread, could you also look into how actions infect the spread, like shutting down words, for instance, and maybe also simulate what would happen if you would do this or that?
That's something that is very, very interesting. And I think one thing is to what would happen. For me, more interesting would be to see like the difference between what would happen, what would not happen, kind of with shutdown, without shutdown. to really show the difference and to show the impact of this type of work. We haven't done it yet. Yeah, that's a good idea. Yeah.
Yeah, but you have access to that kind of actions taking, right?
Yeah.
Okay. Yeah, interesting. This event-based, to include this event-based. Okay, further questions from the audience? Don't be shy. Unmute yourself. Be brave.
I do have one question on slide 73, I think. So I just noted the number. It will probably pop up again when you show the slides, please.
This one? No.
No, I mean, it was a bit before, I think. Oh yeah, okay. I think you said here the scalability issues a couple of slides later. And I was curious, what are really the issues here? Is it the Markov chain multicolor simulations that you can run? Or is it really on the visualization side?
The scalability is on the visualization side. So
okay.
our basically, if you look at this, is the limitation, the screen size is the limit. Not the sky is the limit, but the screen size is the limit. And our approach basically shows each time moment on x-axis, and each page. The worst case is every time moment and every patient needs to be shown.
Yeah.
So basically the screen resolution is the limit. We need something that is more space efficient.
And
or shows the aggregated data, or
Then maybe one follow-up question. Do you think it's sensible? Now you have this very nice graph as a presentation of a model of the environment. And do you think about an automated analysis such that you can track down, I don't know, immediate actions that you have to take, or find some really, what you said, super spreader patients or links? Because you can build the graph.
I'm not sure I understood the question correctly.
But you can build the graph, but you cannot visualize it, right?
Yes.
And then the question is, can you do it
or we can visualize it, but then it needs a lot of scrolling down and up and down.
Yes. And because you have the information, can you process it automatically without human interaction? That's my question.
Yeah, for example, the spreaders, the maxi spreaders, we could identify automatically, yes.
Okay.
Some information we could find out automatically. Not all, but some of them, yes.
Maybe time for one more question. Anyone? If not, then thanks a lot, Tatiana, again for a great talk, for taking the time to join the Zoom call. I think the audience appreciated it. And yeah, for those of you who do the seminar, please keep an eye on like the upcoming events in January. In January, probably end of January, we're going to have the invited talk, which is yet to be determined. So we don't know the date yet, but we will announce it, of course, as soon as we have it. Erich, did I forget anything?
No, perfect.
All right. Thanks for joining.
I would like to thank you for the invitation and your time.
Thanks. Have a nice rest of the day. Bye-bye, everyone.